Um, and to reiterate, his PhD was in computational mechanics from the University of Wales in Swansea, and his BE honors was in mechanical engineering at James Cook University in Australia. And as you can see from his bio, Professor Leonardi has done extensive research in fluid flow, fluid-solid mechanics, fluid-solid interactions, and a lot of work on coal seam gas transport and geomechanics. He and his group of postdoctoral researchers and postgrad students have capabilities in a number of computational techniques, and those include lattice Boltzmann, discrete element, finite element, and finite difference methods. And Chris and his team collaborate extensively with their national computational facilities, such as the POSI Supercomputing Center. And without further ado, I'd like to introduce Professor Leonardi.
Thanks, John. Thanks for the introduction, and thank you everyone for taking time out from your busy days to listen to this presentation. So, as the title there says, I'll be talking about recent learnings from high-fidelity simulations of a very small amount of proppant. When I came up with this title, I thought, yeah, a small amount is a thimbleful, and I ran it past Travis, who's a member of faculty in the school and one of my former PhD students, and he said, well, what's a thimble? And I said, well, you're probably young enough to not really know. And so I asked Windows Copilot to draw me a thimbleful of sand, not proppant, and this is what I got, and it's pretty cool. So I've thrown that in as my title slide. In addition to Travis, I should acknowledge Lukash, Nathan, and Lachlan, various members of my team who've contributed the bulk of the heavy lifting to this presentation. And so without them and without the support of National Computing Infrastructure, the POSI Supercomputing Center, this presentation wouldn't be possible because the computations would not be possible. So with that, I'll keep moving and do what is customary when we gather for meetings here in Australia, and that is acknowledge the country where we are gathered today, well, at least where I am to give this presentation, and in particular acknowledge the traditional owners of the land from where I am presenting, and pay my respects to their ancestors and their descendants who continue cultural and spiritual connections to country, in particular the Yagara and Turrbal people of the area around Brisbane, or Meanjin, as it is also known here in Queensland. So what I'll get through today is a little bit of context about proppant transport in coal bed methane reservoirs or coal seam gas reservoirs here in Australia, give a little bit of detail about the modelling methodology that we use to do these simulations, and then talk through in detail one case where we looked at the analysis of a non-API sand, which is prospectively to be deployed in some coal seam gas hydraulic fractures here in Queensland. And then if there's time at the end, just highlight a couple of other applications that we've used this technology for. And then I'll finish off with some closing remarks. And as John said, it is now after midnight here in Australia. So if the words come out a little bit out of order at some points during the presentation, please forgive me, even though I'm feeling pretty bright. So yeah, so coal bed methane is a little different to shale. We're dealing with reservoirs which are naturally fractured and in the large proportion don't need any hydraulic fracturing for economic production. So the natural fracture network results in sufficient permeability to produce economic rates of production. But where the natural fracture network is not sufficient, wells will be fractured to try and get economic rates of gas out of the subsurface. So we all know what hydraulic fracturing is. I don't have to go through the details on the left. I will say that various techniques have been used to try and improve hydraulic fracturing outcomes in coal seam gas reservoirs here in Queensland, including the use of 100 mesh following pad and prior to a more traditional sand to try and enter some of the cleat network, which is connected to the primary fractures, and also much more recently, the deployment of microproppants to try and also activate that cleat network, which is shown schematically over here on the right. So we've got a diagram of some typical face and butt cleats that you would have in a coal seam, and down in the bottom right-hand side, this sort of like schematic idea that one would inject particles into the primary fracture that hopefully leak off into the cleat network to help stimulate them after the fluid pressure is reduced. And so what do we do to try and understand proppant behavior? As has been mentioned, we do high-fidelity simulations of particle transport in very small geometries. So that's where the thimbleful of proppant comes from. And we do this in such a way that we try to capture all of the relevant physics in the particular problem. So Navier-Stokes hydrodynamics, full frictional contact of particles, and the boundaries or the fracture in which they flow, fluid rheology, any electrostatic forces that might be present as well, and do simulations that look like this animation here. Hopefully it'll, whoops, it's not played for some reason. I'll try that again. So yeah, this is just a rendering of one of our simulations. We've got a primary fracture with some branching cleats, and then we start injecting our proppant suspension. We see leak off, and we see occlusions forming at those leak off points because of the drag of that fluid in part on the particles near those cleats. And we can use this type of model to study a whole bunch of things, including size segregation, migration, particle leak off, and ultimately the retained pack and pack permeability in our fracture. So particular questions that we've asked of this type of modeling include, if you have a wide size distribution of particles, how do those particles self-organize? How do they migrate? How do they segregate? What drives clogging and screen out of proppant and under various solids loadings and fracture textures? What's the retained permeability after closure or conductivity and embedment? How do particles leak off into cleats? What's the optimal carrier fluid rheology? And the focus of this talk will be how would a non-API proppant be expected to perform during placement and then production? So I'll talk very quickly about the modeling technique that we use here, where we're using the lattice Boltzmann method to simulate the fluid mechanics and the discrete element method to simulate the particle mechanics. For those of you that don't know, LBM's a traditional, a fairly mature alternative to conventional methods for modeling fluids now, where the traditional methods discretize the Navier-Stokes equations. What we do in the lattice Boltzmann method is we discretize an averaged form of the Boltzmann equation for statistical mechanics. And instead of solving, PDEs like Navier-Stokes momentum and mass conservation equations, we solve for the propagation of particles of mass that move around on a grid and collide with one another. And at the macroscopic scale, that mesoscopic model actually emerges to give us a Navier-Stokes type hydrodynamic model, which is very useful because we can implement it on a regular orthogonal grid. It's very straightforward to map complex boundaries on the lattice Boltzmann method grid. And therefore, we can incorporate a large number of irregularly shaped particles. We can couple those in. And we have some serious advantages in terms of locality of computation, which means parallelization is relatively straightforward. And we can really make good use of not just single GPUs, but multi-GPU clusters, which are beginning to dominate the high-performance landscape in the big compute machines worldwide. So LBM is actually used quite widely in industry now, a lot for vehicle aerodynamics. The major CFD packages have got their own lattice Boltzmann solver implemented in them now. And so it's no longer a niche technique, it's actually quite widespread. And for the particles, we use the discrete element method. This is just an example of something I did in my former life as an engineering consultant nearly 20 years ago, now using DEM to solve a bulk materials handling problem in a cold transfer chute. But it's also now very well established. So you can get a DEM solver in Siemens analysis tools or in ANSYS. And so it's used widely in bulk materials handling problems, but also in geomechanics, where we're dealing with the fracture and fragmentation of rock type materials. So one of the good advantages of DEM is it's very straightforward to couple it to the LBM, as I've already mentioned, and simulate particle suspensions at high fidelity. So what I mean by that is we're fully resolving the pressure field around a particle so that we capture the drag and lift quite well. And this just highlights that point. So when I say fully resolved, or when I say direct numerical simulation, what I mean is that schematically here, if our grid, our LBM grid, is these orthogonal lines here, this circle is one of our particles, and it shows that each one of our particles is actually mapped to a large number of LBM grid nodes, as opposed to what might occur in other CFD DEM type applications where the particles are much smaller than a cell. Here, it is the opposite. And so what that implies is that these computations, even though they are physically quite small, are quite expensive. And so we're using significant amounts of compute time to be able to generate the results that we are generating. If you're interested in how this works in a little bit more detail, the code that we publish is open source, so TCLB, and if you just search tclb.io, you'll find our website, where there's a whole bunch of papers that describe the mathematics and also allow you to download the software and play with it for yourself. Right. So with that said, I'll get on to the case study that I wanted to talk about, and the problem was brought to us by an industry partner who were looking at using a locally sourced sand that was cheaper than the product that was coming from interstate, but less favorable in terms of its shape and its size distribution. And so I just refer to it here as a non-API sand because it does not meet some of the API standards, particularly on particle shape. But there's a photo in the bottom left that shows you what it looks like. So it's quite angular. There's quite a wide size distribution. And you can see the size distribution also up here on the top left. And so just for comparison in terms of roundness and sphericity, you see that in comparison to a Wisconsin sand, which has got a really quite nice spherical shape, the roundness is significantly lower and the sphericity is lower as well. So our partner was interested in how is this stuff going to flow in a fracture? Is it going to enter the branching cleats to help stimulate those? And once it is packed in the fracture, what's it going to mean in terms of fracture conductivity? So the way we go about analyzing this problem, as I've mentioned, is we study this at a very small scale, but we start with a fracture geometry that we generate from a power spectrum model, which was originally sourced from the literature. And we've modified to take advantage of some imaging we've done on some rock surfaces here. And so with this power spectrum, we're able to generate lots and lots and lots of different realization of fractures based on 3 parameters. So it's the power spectrum, it's the surface correlation, and the distribution of roughness. And so we basically can control the long wavelength tortuosity of the fracture, and then the short wavelength roughness of the fracture surfaces, and then how well they're correlated. And so if they're perfectly correlated, that means the 2 surfaces of the fracture are parallel at all times, but when they become decorrelated, they are no longer necessarily parallel. And so what we can see here on the right-hand side is one realization of a fracture that has a mean width of 0.5 millimeter and a mean roughness of 20 micron. It's perfectly correlated, so our correlation coefficient here is 1. and a number of other realizations as well. So this is a 0.5 millimeter fracture with a roughness of 10 micron. This is the same fracture with a roughness of 20 micron, and then a roughness of 20 micron with some decorrelation. And so as we continue to decorrelate these fractures, they actually will touch in certain places. And so we end up with something that could be a fracture that has been dislocated due to shear, or changed due to some mineralization that's built up inside the fracture. What's really nice about this approach is that we can run, say, multiple repeats of the same analysis and generate statistics on our results. So rather than just generating a geometry, running it in our analysis, and then listing one particular result, what we can do is run 10 or 20 different realizations of the same statistical description of a fracture, and then get a distribution of what the results look like. Then how do we deal with our non-API sand? On the left, we have some convex hull representations of our non-API sand, which is capturing the angularity quite nicely. The issue with dealing with a discrete element that looks like what we see here on the left is that the contact search and contact resolution is really quite expensive. And so to solve a problem using particles like this over millions of time steps would become really quite expensive. And so what we do to get around that challenge is model the angularity of the particles using clumps of spheres that you can see here on the right. So we've got linear, two-dimensional, and three-dimensional clumps. So there's kind of lines, triangles, and tetrahedra comprised of spheres, as you can see, and we adjust their angularity by adjusting these dimensions. So A being the spacing between the particles at the extremities of an edge, the spheres at the extremities of the particle's edge, and R as the radius. So one thing to note with these particles is as they get more angular, we keep the volume the same, where all of these particles have the same volume. So we keep that constant, but their angularity increases as we increase this ratio, and their sphericity and roundness decreases. And so by using spheres to build these angular particles, it makes our computations tractable. And then what does an analysis look like? It looks something like this, where in the top left, we've got spheres, and then we've got our linear clumps in the top right, our 2D clumps in the bottom left, and our 3D clumps in the bottom right. So we've got a fracture here, which is got a width on diameter ratio of about 3. And so transport is generally pretty good, but you can see, particularly in the 3D clumps, that there is some impediment to flow due to the way that they interact with the walls and they interact with themselves. So whilst this might be nice to look at, it doesn't really tell us much. It's certainly not quantitative in terms of what the behavior is that we're seeing there. And so what we do to interpret our results is look at them in the context of other empirical models that exist in the literature for suspension transport and also screen out. So there's a bit to talk about here on this first slide for the linear clump. So I'll take my time and say the first thing is we've got 3 graphs. We've got a graph on the left where W on D is 2.1. That's the width over diameter ratio. And remember that D here is the diameter of the equivalent sphere volume, or the equivalently volumed sphere. So that's our measure of particle size. As we go right, our fracture gets wider. So W on D is 2.5, and then W on D is 3. What we're graphing here is the flux or the flow rate compared to the cubic law. So cubic law for flow between parallel plates versus the volume fraction. And so you can see immediately that as we get to a volume fraction up around 0.6, we've got no transport. We're at the theoretical packing limit for spheres. And so our suspension is certainly not moving up at that solid volume fraction. What we've also got plotted here is Krieger-Doherty type model using the Marin-Pierce suspension viscosity as a correction for what the viscosity of that suspension would be at a certain solid volume fraction. So that's the dashed line here. And in red, we've got this screen out criterion, which we believe should be originally attributed to Smith and Schuyler-Poversky, if we follow the literature back. Which basically says that for a ratio of width to diameter at a certain solid volume fraction and assuming a parameter b, that there is a point at which the transport will screen out and our fracture, our suspension stops moving. And so for this case, that line is shown here in red. We've also got the Kozny-Kármán equation based on spheres in the dotted line here as well, which is typically used for the permeability of a pack of spheres. Now, our simulation results are shown with the circles, the triangles, and the diamonds, and the solid lines in between them. What they correspond to are different A/R ratios, so ratios of the side length and the sphere radius. And so what we see as we go from spherical particles to particles that get longer and longer, our behavior deviates further and further from this Krieger-Doherty model with the Marin-Pierce suspension viscosity. What we also see down here at the very high solid volume fractions is that our results basically match perfectly with the Kozny-Kármán relationship, telling us that we've got down here, we've got a static pack of particles, it's not moving, and its permeability is equivalent to that which would be predicted by Kozny-Kármán. So what we also see, and this is one of the really neat things that we found, is that in all cases, the relationship between permeability and solid volume fraction is continuous, no matter what we do. And we don't ever see this discontinuity in flux that you would expect from this type of screen out criterion. Whilst you would say that the drop in permeability or flow rate is quite severe, say between 15% and 30% solid loading, there is no point, there isn't a distinct shutdown in transport. So then as we get wider, what we see, which is also interesting, is that the results from our simulations all collapse on one another. So our A on R ratios of 0, 1, and 2 are basically all the same, telling us that the degree of particle angularity has become unimportant as this fracture has gotten just a little bit wider, not significantly wider, just a little bit. And that's also true as we get wider again. The results are all effectively exactly the same, but in no case does the behavior match what you would predict with this Krieger-Doherty model with the Marin-Pierce suspension viscosity. So then if we go to our 2D clumps, we see similar types of trends. We see the fact that as the fracture gets wider, the influence of particle angularity effectively disappears. That's true for this width on diameter of 2.5 and of 3. But over here in the narrow fracture is where we see the interesting behavior in this 2D case. And here it's interesting because our circles here represent spheres, and our triangles represent an A on R of 1, and our diamonds represent an A on R of 2. What we see is that for A on R of 1, the flow behavior is worse, and then it gets a bit better as A on R goes from 1 to 2, which at first interpretation is a little unintuitive, but the way we see this manifesting is that there is a degree of particularly for these planar shapes, where they align themselves with the flow streamlines and actually flow better than spheres or particles that get longer again. So there is for a certain shape, particles that align themselves quite nicely with the flow and therefore have higher fracture permeability But as we get longer again, we expect that permeability would drop off again, and we'd start to see a drop in performance. Now, there's a couple of questions in the chat. I might leave these to the end because they're quite substantial questions. So I'll come back to those. Right. And then we've got our results for 3D here, where we see the most degradation of fracture permeability because of the angularity of these particles and the three-dimensionality of their nature, or the nature of their three-dimensionality. And so we also see this influence of angularity disappear as as our fracture gets wider again. And so in summary, really where the particle angularity is most important is in narrow fractures. So this is at fracture extremities, or as is the case for calcium gas production or stimulation, in the cleats that we're hoping to have some of these particles enter. So where W on D is 2 or even less, we would expect really quite poor entrance characteristics of these particles, just due to the way that they transport in narrow fractures, and particularly as their local solid volume fraction increases, their impediments to flow would also increase as well. So that's the transport part. The next part is, if I can get it to progress, is how the packs behave once they're sitting in a fracture. And so what we've got here is, again, rendering of 3 different particle types. So we've got our non-API sand here. We've got our Wisconsin sand here. And for reference, we've got some spheres, a sphere pack over here on the right-hand side. And what we've done in this part of the work is flowed 100 mesh through these packs to determine their percolation characteristics and their retained conductivity. So we create a pack out of these different proppant types, including our non-API sand, and we flow some 100 mesh through it to see how things permit particle entry and then strain particles midway through the pack. Before we did that, we looked at some statistics on the pore size distribution. So we've got our non-API sand here over on the left, and we've got our Wisconsin sand here in the middle, and we've got our spheres over on the right. So for our spheres, as you would expect, the pore size is very tightly controlled, like focused around one particular number, because our spheres are all similar in shape, obviously, and quite close in size. But if we look at our non-API sand over here on the left, we've got a much broader distribution of pore sizes, meaning that we have some quite large ones and some quite small ones, and a fairly big, a relatively broad distribution between those extremities. And that has implications for allowing particles to enter, but then also excluding them at some point throughout the pack. And so we see this in the data that we generate from these analyses. What we've got here is a plot of the percentage of total deposited particles versus the depth from the top of the pack. So if you imagine that this is the left-hand side is the top of the particle pack, where particles are entering here from the left. We see here that our non-API sand, which is these yellow stars, is permitting significantly more particles to enter the pack than our Wisconsin sand or our spheres. Those are shown, the Wisconsin sand is with the triangles and the spheres are with the circles. And what we've got here is a reference solution from the literature, which is based on experimental data with spheres. So first thing we can say is that our model result for spheres is reproducing a result from the literature. So that gives us good confidence in what we're doing. And then it gives us confidence to interpret what we see from this non-API sand as being some quite different behavior, as being a much greater proportion of fines type particles being permitted into the pack. Then when we look at what that means in terms of retained conductivity or pressure drop, what we've got here is a plot of head loss ratio versus specific deposit. Now, specific deposit is the ratio of deposited particle volume to packed volume. And so what we see here, and we've also got a reference solution from the literature showing that for spheres, our simulations are matching that solution almost perfectly, which is fantastic. But what we see here is that the non-API sand shows about a 26% higher relative head loss than the spherical pack before major filter cake effects dominated. And we see that up here where the results start to deviate from this empirical trend here. So if we look at the way the non-API sand results sit quite above, noting that this is a logarithmic plot, we can see that because this type of particle pack permits much more particles to enter, but then excludes them or filters them out at some point, it will, over the longer term, potentially show greater decline in conductivity as the years go on and the wells and the fracture continues to produce. And so that's a particularly interesting result for our partners and their decision in terms of what they use as their primary proppant in their hydraulic fractures. So that's the end of that case study. Before I finish, I just wanted to touch briefly on some other applications. If you saw my presentation at ARMA, you will have seen these slides before, so I'll only spend a few minutes talking about these, but they're interesting nonetheless for what we can learn from simulations of a very small, very small section of proppant transport in a fracture. So the first one was motivated by the transport of microproppant in hydraulic fractures and ended up showing some quite interesting results in terms of particle migration and size segregation. So one of the challenges with a microproppant is quite poor size control. So particles can range in a commercial product anywhere from on the order of 2 to 3 microns up to 60 or 70 microns. And so you've got, by virtue of the product, a fairly wide size distribution that you're pumping into your fractures. And what we did from an analysis point of view was actually just flowed that material in a channel that's periodic in the flow-wise and transverse directions to see how these materials organize themselves over time. And one of the really interesting things that we found was the smallest particles in that suspension would end up migrating to the center of the channel if the solid volume fraction was sufficiently high to limit the shear fluctuations of the larger particles. So at solid volume fractions of around 30 or 40%, which will occur after you have some local settling within your fracture, we get this behavior where the smallest particles, which we would ideally like to have off at the channel walls, leaking off into cleats, end up making their way into the center of the channel, which is exactly where we don't want them to be. And so this was really quite an interesting result for us that we published a couple of years ago now. One of the other things that we've done was looked at clogging in narrow fractures from a probabilistic point of view, where we do small scale simulations in synthetic rough fractures and change the solid volume fraction to test at to determine the probability of screen out occurring or clogging occurring, I should say, at a particular solid volume fraction. And so with this type of analysis workflow, what we do is we vary the solid volume fraction, which you see here on the x-axis, and calculate the probability using a logistic type regression model of clogging occurring. And so for each of these solid volume fractions, what we would do is actually run a number of realizations, so repeat tests, and the more repeats that we run as we go from the left to the right, the tighter the distribution of outcomes becomes. So we settle around a mean and our standard deviation becomes less and less. And so what we see when we interpret, I should say, these numbers here, so the phi5 and phi95 number, so that's the solid volume fraction at 5% chance of clogging, and the solid volume fraction at 95% chance of clogging. If we then plot our results a little bit differently, so we plot the phi5 line, that's the squares, and we plot the phi95 line, that's the circles, at different W on D, what we see is the ratio changes. Well, the clogging behavior changes with W on D. We don't have a consistent ratio of width to diameter at which we would expect clogging to nucleate and start screen out. We actually see from a volume fraction of around 20%, it actually drops off as we get to W on D about 1.8, and then it increases. And our explanation for that is that we go from monolayer transport, where there's no possibility for arching to form between two particles, I should say, to then here a high probability of two particle arches forming, which is why our solid volume fraction to require clogging drops off. And then as we get wider again, those two particle arches can't form stably, and we start to see the W on D or the solid volume fraction increase as our width gets much greater. What we also show is the influence of electrostatic forces, remembering that in this microparticle suspension, there are some particles that will be affected by DLVO forces, and we've implemented that in our solver and shown that as we increase those particle wall interactions, as you would expect, the solid volume fraction required for clogging to occur starts to decrease quite dramatically. So as we increase that electrostatic adhesive force, clogging starts to occur at lower and lower solid volume fractions. We've also done some work which was presented in this paper here, and is also now in a manuscript under review, looking at leak-off and fracture occlusion, where we have Newtonian and non-Newtonian carrier fluids. And what we found from this analysis, and this has been corroborated by some tests that were done by StimLab back in the 1990s, is that these microproppants probably actually act quite a bit better as a fracture diverter than a stimulator of remote cleats, because for the right combination of particle size and fluid properties, we can actually close off these branching cleats quite nicely and concentrate our flow within our primary fracture. So with that, I'll finish up, and I'll just say a couple of things about where we're going next. So in terms of our fracture generation, what we have started doing and we would like to do more of is informing our power spectrum with actual images of rock textures. So being coal, a sedimentary material, the fractures that form vertically, so those desiccation cleats, have quite a different texture to those that are horizontal in the plane of bedding. And this changes with the maturity of the coal as well. So what you see here on the bottom left is a digital optical microscopy image of a fracture surface from a coal sample, which we can then process for the power spectrum and use that to then generate realizations of fractures. This particular coal image here is a little bit challenging because it's kind of smooth, and then it's not. We have these quite distinct discontinuities which don't necessarily fit with the fractal or self-affine model of the power spectrum, but nonetheless, it gives us some data which better anchors our fracture geometry. And then the next thing, which is kind of obvious, is how do we upscale the kind of behavior that we see in our small scale simulations to something that's much larger, like you see in this video here. And so Lukasz and I have started developing some techniques for taking the data that emerges from our high-fidelity simulations and using that to populate a model that is not your traditional convection equation for suspension transport, but appears to show some promise in terms of large-scale simulation of proppant transport. So what we've got here is a suspension being injected in the left of this square slot, and flow exiting at the top right. And what you see here in red is the accumulation of particles forming a bed in this fracture. But this is very preliminary work, and early next year we hope to be able to present more formally on this work. So with that, I'll leave it there because that's my last slide, and I will open it up to questions.
Thanks, Chris. Fantastic. Maybe I know you can see the chat. Maybe you just can walk through the chat. If you don't mind sort of paraphrasing the question, it would be great.
Yeah. I might, so I'll go here. First one, is this model used to match the pressure trend in commercial fracture stages with SLB rod-shaped proppant or Hall interlock proppant? No, I haven't done that. I haven't tested any Schlumberger rods or Hall interlock proppant, but it's something that we could do. And I'd have to look up where I might find that data. But it sounds like an interesting problem and a really good further validation case for what it is that we're doing.
Well, we don't want to let you off the hook so easily. Can you speculate what you think might happen with a rod-shaped proppant configuration?
So a rod-shaped proppant is going to behave very similarly to the linear clumps that we've been modeling. It would just be at a greater aspect ratio. What's going to happen? There will be this behavior where at a certain aspect ratio, the particles align themselves with the streamlines and they actually transport quite nicely if the solid volume fraction is not too high. But it doesn't take much to perturb that behavior. So it can be perturbed by fracture roughness or fracture tortuosity, or it can be perturbed by the particle length becoming quite significant with respect to the scale of the roughness. So there would be a point, I would imagine, when the solid volume fraction gets high enough that these things, I would say these things start to get impeded quite significantly in terms of their transport.
Yeah.
So the next one is slide 18. You mentioned no abrupt shutting down of flow observed. If your model could take into account much more angular features, sharp edges, perhaps the transition may be more abrupt. That's a really good observation. And it's one that I've talked about, because even though we do have some angularity synthetically modeled in our particles now, we don't have those really sharp corners like you see in a sand. So it's a good observation, and it's one that I would like to test, because we were genuinely surprised by the continuity of the relationship, and even looking at interrogation of the flow in some quite high solid volume fraction situations, there would be persistent particle transport in amongst almost stationary particles, but almost no evidence until we got to very high solid volume fractions of complete screen out. Okay. Have I seen the paper unifying suspension and granular rheology? Yes, I have. I mean, that's a very famous paper in granular rheology. Nice experimental data on suspension rheology for spherical particles. It would be nice to run simulations to see if they match experiments for validation purposes. So that's a good point. We have done numerical rheometry quite a while ago. So when we first started working in LBMDM modeling for proppant transport, one of the first works we did was on simulating a numerical rheometer, where we would just shear a suspension between two parallel plates, like a Couette type flow cell, and we would match the data very, very well. It was quite good, and And further to that, we've also validated the transport stuff against experiments for transverse migration. So there's a really famous paper by Leon and Leal where the transverse migration of particles due to inertia and due to shear is measured, and we've demonstrated with our, I don't think I have the slide in this presentation, but we've demonstrated that we can match that transverse migration really quite well. So we feel pretty confident that we're capturing the mechanical and hydrodynamic components of those migratory behaviors. As Igor mentioned above, is there any reference experimental study to find out the average diameter to width ratio of deep coals in Cooper Basin or CSG? Yeah, I think that's a question about cleat width. Is there data on that? There is. Those data come from samples that have been taken to the surface. So once that happens, they kind of start to change irrevocably, right? So gas is desorbing, matrix is shrinking, pore pressure has changed dramatically. Some of the coals, the most cleated coals, will actually disintegrate fairly quickly once you take them to the surface. And so people do try to measure cleat widths, and one of my colleagues is actually quite good at doing that using digital image correlation, I think it's called DIC. So yes, we do have measurements on cleat widths, and that width on diameter ratio can be anything from 1 or less to say 2 or 3. So the ratios at which we're simulating these things are fairly representative of cleats, not the primary fracture. The primary fracture is padded out to be a few millimeters wide, and so things behave themselves quite nicely in that situation. But it's those cleats that we want to try and stimulate where we see the problems occurring. Also in slide 23, what are the units of permeability we are talking about? So there are no units of, it's just a ratio of the fracture permeability to the equivalent cubic law. So you can think of it as a normalized fracture permeability. So for that particular fracture width, you would be able to calculate from h on cubed what your fracture permeability is, and also the viscosity of the suspension, the corrected viscosity of the suspension. Here, we're just presenting the normalized value of permeability that's normalized by that cubic law permeability. What types of fluids can you model? Yes.
Sorry, Dr. Chris. Sorry, can I interrupt you for a minute?
Yep.
Okay, so the question was raised by me. I am Asad Pirzada. I am working with CentOS as senior geomechanics geoscientist right now.
Oh, yeah.
Okay, the thing is that you're comparing it with the ratios above 2.1, and I personally think that it's quite smaller than this one. As you said, it's 1 and 1, 2, and 3 and stuff like that. And even the cleat size which we see on the surface is itself being opened up with the adsorption of the gases.
That's right. Yeah, and so that was the point I made at the very start, is so once you take a sample to the surface, the gas is desorbing at a fairly rapid rate. The matrix is shrinking to some degree, and the cleats are changing, right? So yes, it's a difficult thing to quantify.
So is there a plan to do it on a smaller scale than this one, like or smaller than 2.1?
Oh, I mean, we certainly can do, and some of the work that we've done previously, but that was done with spherical particles, was at ratios much closer to 1.
Perfect. Thank you so much. Completely answers my question. I hope to see you soon somewhere.
Yeah, I'm surprised we haven't met before.
Yeah, I hope to see you soon.
Yeah.
Thank you.
So what types of fluids can we model? We do Newtonian, obviously. We do power law, shear thinning, shear thickening. We do Bingham, Herschel, Bulkley. We do Kwong Low. That was for biological applications. We haven't got a viscoelastic implementation, but I have a student starting on that pretty soon. So we've got a wide range of rheologies implemented. What diameter are they using for the size distribution on the non-spherical particles? Is this based on average diameter of the particles, smallest diameter, or some other method? Assume that the standard SIP analysis would give a distribution based primarily on the smallest diameter. I'm not quite sure who they is. I assume they is us. Size distribution on the non-spherical particles. So in these angular particles that I presented the results for, they're primarily monodispersed, so they're all the same size. When we've done work with spheres before, and even in the convex hull particles that I showed, there was a subset of the distribution modeled. When we've previously tried to simulate 100 mesh, what we do is we capture the range between, say, 100 and 200 micron, with a mean around 150 micron. But here for these angular particles, they're largely the same size. Okay. Proppant crushing and embedment to the fracture surface are an important component of fracture conductivity. This is true. Proppant size distribution and angularity plays a strong role in this. Is it possible to evaluate this with this software? The results would be very different. So not with this particular solver, but with a finite element code, yes. We've previously done some work looking at embedment of proppant in coals and what that means for retained conductivity. And we did that using elastoplastic finite element modeling as an extension to some mathematical modeling that had previously been done at the University of Adelaide. So yes, in principle, that's all very possible. It's not something that we've done though, but we would have the capability to do it and look at how these things embed under closure stress. Okay, so first part of the talk addressing the non-API sands showed individual curves, fracture permeability, and so I assume these are individual simulations. Have you done any stochastic simulations to add error bars to these curves? Can you comment on potential confidence intervals in these results? That's a really good question. So yeah, so for these results on the non-API sand that I showed, those haven't had multiple runs done for each realization, and the reason for that is that the compute time required is fairly significant. So we've generated the full curves. We haven't generated the distribution around the results. But as you noted, in the later results on probabilistic clogging, what we were able to show is that, you know, with 40 repeats of a single simulation, we actually get the standard deviation quite low. So the uncertainty reduces to quite significantly once we run 40 repeats. But 40 repeats is easy to say, but compute-wise is a significant number. I'm trying to think if I can give an indication of how much compute time that would actually mean. And it could be that if we were to do the full stochastic analysis of the results that I've shown here today for angular particle transport, that it would consume our annual allocation of HPU compute time to generate one graph. So we have to be a little judicious, I suppose. But it's a good observation. Can fluid loss into formation face permeability be modeled versus loss into cleats? At the moment, no. We're not looking. We're not capturing any fluid loss into the coal matrix. We think it's dominated by the loss in the cleats. They're just far higher permeability than the porosity in the coal matrix that we don't capture it. And thanks for the great session. So thanks, Mohammed.
And let me echo that. Thanks for the great session. That was an excellent session, excellent questions. And Chris, I'd like to thank you sincerely for all of us. A great talk.
Yeah, John, thank you very much for the opportunity, and thank you everyone for that. They were really great questions. So people were listening. So that's good.
All right, thanks everyone. We'll see you in a couple of weeks. A couple of weeks actually is going to be a good session. Look out for an announcement on that.
Oh, that's going to be the
This
battle.
was-
That's going to be the battle, isn't it?
Yeah, it'll be controversial.
Yeah, it should be good. All right. Well, thank you, everyone. And
Thanks all.
yeah, good morning from Australia.
See ya. Hey Chris, that was awesome. As a matter of fact, I am gonna look for TCLB. One of the fracs that we just pumped at Forge was a blend of 100 mesh sand and a lightweight proppant with specific
Right.
gravity 1.06.
Oh,
And
wow. Yeah.
This, the intent there was to inhibit settling,
Yeah.
because in this granite, those fractures will stay open forever.
Yeah.
And it actually may have worked, because we did find some of the lightweight proppant had made it to the production well. And so if you're ever looking for another challenge, there's a good piece of there's one, and I think we'll try it.
Yeah. So that's actually a really cool one. I've never heard of that mixed buoyancy type application before. But yeah, it'd be something that we'd be really interested in having a look at.
Well, if that's the case, I'll send you some data.
Yeah. Sounds really good.
Very good. Well, time for bed, man.
Yeah. I got to take my son camping tomorrow morning. I got to go to bed.
Okay, well, have fun with that too. We'll see you.
See you then.
Bye, everyone.